Hey guys, welcome to the first ever TRI STEM lecture. My name is William and I'll be your presenter today. Today I'll be talking about the topic of fractals and dimensionality. So this is a two-part lecture and today I'll be presenting part 1. Let's start with a brief history of fractals. Fractals were developed by Polish-French mathematician Benoit Mandelbrot. He is famous for his studies on chaos and recursion, both topics that are very similar to fractals and relate to fractals in some way, shape, or form. So what even is a fractal? Fractals are never-ending geometrical figures where inherently self-similar patterns recur at progressively smaller scales. As you can see on the right side of the screen, the Mandelbrot set, the fractal that you guys saw on the title screen, is a perfect example of a computer-generated fractal. It is inherently self-similar and it is always recurring at progressively smaller scales. Now, moving on to a very important concept of fractals, scaling recursion. As seen in this photo, you guys can see the Sierpinski triangle, another very famous fractal. As depicted by the diagram, the zoomed in portion of the Sierpinski triangle is actually the exact same pattern as the original Sierpinski triangle. This explains the self-similarity and the scaling symmetry of fractals. As seen in this diagram, fractals are composed of smaller copies of themselves. They show the same pattern when smaller scales are magnified. Other very famous fractals include the Sierpinski triangle, which is the example that I just showed you guys, but that was a modified version, and the Koch snowflake, which is another very famous fractal. Now, moving on to a very important concept of fractals, the dimensionality equation. So, D represents the dimensionality of a fractal, which is essentially a measure for the complexity of change of a fractal on its current iteration. N is the number of self-similar smaller shapes required to create that iteration of the fractal, and S is the current iteration of the fractal. Both N and S have to be positive integers. Now, these concepts are not intuitive at all, so don't feel worried if you're kind of confused right now. I'll be leading you guys through a couple of examples to help you guys better understand the concept of dimensionality. As seen in the photo on the left, the first iteration of the line fractal is represented by line A. The second iteration is represented by lines B and C being combined together to form a bigger line. Since lines A, B, and C have the same length, we know that the second iteration is composed of two smaller self-similar figures. Therefore, n of the line segment fractal for the second iteration must be 2. And since we are on the second iteration, s must be 2 as well. Therefore, dimensionality of a line or a line segment must be 1. Now this makes sense because a linear line is a perfect representation of one-dimensional space. As seen in the photo on the right, square A is the first iteration of the square fractal. It has a side length of 1 and it is a 1 by 1 square. On the third iteration, the square fractal has a side length of 3 and it is a 3 by 3 square fractal. However, here's the twist. As we all know, there are 9 squares inside this fractal structure. Therefore, n in this case must be 9 because 9 smaller squares are required to create the bigger square fractal. However, since we are only on the third iteration, s in this case will be 3. Therefore, the dimensionality of the square fractal for its third iteration must be log 9 over log 3. Since we know 9 is 3 squared, log 9 would then be log 3 squared. Log 3 squared over log 3 would then be 2. So therefore, the dimensionality of the square fractal is 2. Now again, this makes a lot of sense because dimensionality on a two-dimensional plane must be 2, and square coordinates or coordinate planes are perfect representations of a two-dimensional area. Now I have a sample problem for all of you guys to solve. As you can see in this photo, there are 2 iterations of the Sierpinski triangle, the first iteration and the second iteration. So I want you guys to calculate the dimensionality of the second iteration of the Sierpinski triangle. Remember to consider n, the number of smaller self-similar figures required to create the current iteration of the fractal, as well as s, the current iteration of the fractal. And also know that dimensionality is log n over log s. Furthermore, keep in mind that color is very important in this case, so please consider the individual colors of the triangles themselves. Now that time is up, let's look at the solution to this problem. As seen here in the second iteration of the Sierpinski triangle, there are 3 black triangles, which are the self-similar patterns that are smaller and create the new pattern. Therefore, n in this case will be 3, because the original pattern is a black triangle. Therefore, we are not counting the white triangle in the middle of the second iteration. This is why n is 3 instead of 4. And since we are on the second iteration, s would be 2. Therefore, the solution to this problem is dimensionality equals to log 3 over log 2, which is approximately 1.584. Now, you might be wondering why dimensionality isn't a positive integer. Well, this is completely possible because on different planes and on different fractals, there could be different complexities of change, and they don't necessarily have to have dimensionalities of positive integers like the square plane, or the square fractal, or the linear fractal. So this is why fractals can have dimensionalities that aren't necessarily positive integers. They just have to be positive rational numbers. So therefore, as seen from this example, dimensionality does not have to be a whole number. So you might be wondering, how does the concept of dimensionality connect to fractals? Well, this is a pretty easy connection. As previously stated, dimensionality is a ratio of change in detail to change in scale. The larger the dimensionality of an iteration, the larger the amount of change would happen to that iteration of the fractal. Hence, mathematicians use the concept of dimensionality to describe the complexity or the drasticness of change in each iteration of the fractal. To summarize what we learned today, fractals were developed by Benoit Mandelbrot, and they are often created by computer programs because they are inherently self-similar and never-ending. Furthermore, fractals are shapes that have recurring patterns at progressively smaller scales, and remember, fractals are always going on. They never stop. Now onto the concept of dimensionality. Dimensionality is a ratio of change in detail to change in scale. The dimensionality of a fractal determines its complexity of change on a specified iteration. Remember that the larger the dimensionality, the more complex the change would be on that specific iteration of the fractal. So now that you guys have a clear understanding of dimensionality, we will be moving on to more fractal discussions and calculations in the next episode. The next episode will be featuring fractal calculations that involve geometry and algebra. We will be learning to calculate the area and perimeter of sample fractals through the use of series and sequences. Furthermore, we will also be discussing how fractals are in real life and how they can be applied to real life situations. Fractals are often seen in things such as nature, plants, and even the stock market or even medical uses. So stay tuned for that episode. Thanks for attending today's lecture, and we hope to see you in future videos.